So we spent a lot of time talking about covalent bonds, a little bit talking about ionic bonds, and we have to get back to the metals. The electron C model. So metals have low ionization energies. This is why they make cations when they react. In a metallic solid, each metal donates valence electrons to a pool, an electron C. So we can think of sodium metal as being a bunch of sodium ions surrounded by a sea of negative electrons. The sodium ions are held together by their attraction for that negative C. So this model explains why metals conduct electricity. For electrical conduction, you have to have charged particles that can move. The electrons in this metal are not tied, those electrons in the pool are not tied to specific atoms. And so they can move, and they do. It also explains malleability and ductility of metals because the attraction in this metal is not directional. Ionic compounds have very high, covalent compounds are very directional bonds. In ionic bonds, the distance between the two atoms is very significant, and so if you hammer a piece of sodium chloride, it's likely to shatter because you're disrupting those bends. Here we have totally non-directional attractions, and these can accommodate deformation. So if you dent this, if you hammer it, they can just move, and it's flexible. It's not like flexible like rubber or something, but it can move without totally losing its grip on the other atoms. And then we've got this guy sort of tacked on at the end. Yeah, question? It's pretty much just the valence electrons that go out into the pool, yeah. Ozone is important, right? Because we're all familiar with the ozone layer, right? And there's concerns about holes in the ozone layer and it getting thinner and stuff. So let's just talk real briefly about ozone. So oxygen, O2, has a double bond, right? We've done that. There's the Lewis structure for oxygen, and we've looked at the Lewis structure for ozone as well. Ozone has resonance, and one way we can represent that is by sort of doing a 1.5 bond here. We can't really show lone pairs that way. But these bonds, it was a double and a single, and so it's actually an average of those two. These bonds are intermediate between single and double bonds. They're going to be weaker than double bonds, stronger than single bonds. So what happens in our atmosphere is there's a lot of ultraviolet light coming from the sun, along with all the other light as well. This UV light is strong enough to break the bonds in ozone, these 1.5 bonds, but not strong enough to break the double bond in the oxygen molecule. So an ozone molecule can absorb 1 photon of UV light. When it does that, it breaks into oxygen and an oxygen atom. The oxygen atom isn't stable, and so these will recombine and reform the ozone. So the ozone is absorbing some of the ultraviolet light, which is a really good thing because we've already got plenty of ultraviolet light. Any questions?